The following content is provided by MIT OpenCourseWare under a Creative Commons license. Additional information about our license and MIT OpenCourseWare in general is available at ocw.mit.edu.
Afternoon. Hope you had a nice weekend. Did you have a nice weekend? Good. Okay. Today we're going to start talking about the motion of molecules. And so we're first going to talk about the translational motion of molecules today and Friday. And then we're going to talk about the internal motion, in particular the vibrational motion of molecules and their rotational motion. That'll be early next week. All right, so first, translational motion. Well, certainly the quintessential equation that represents the behavior of gases is, of course, the ideal gas law. P equal N over V times RT. This equation accurately represents the behavior of gases at low pressures. It is an empirical law, of course. It is a law that Boyle and Charles discovered by doing experiments. They noted that as the temperature is raised, the pressure went up. They noted as the number of the amount of gas or the number of moles of gas added goes up, the pressure goes up. They noted that as the volume of their gaseous container goes up, the pressure goes down. So literally, this is an equation established by experiment and just varying one variable at a time. And since it looked like the pressure was directly proportional to the temperature, well, they wrote an equation where it was directly proportional to the temperature, etc. And the proportionality constant here was always this one constant R, no matter what gas you had. But this ideal gas law here, what it does is to describe the macroscopic properties of a gas. And what I mean by macroscopic properties are properties that describe a collection of molecules. So for example, to really talk about a pressure, you have to have a collection of molecules. Now we're going to talk about the pressure due to one molecule, but that's really just a model. If you want to talk about pressure, you need to have a collection of molecules. If you talk about temperature, temperature really only has meaning when we have a collection of molecules. But what we want to understand is what are the underlying microscopic phenomena that give rise to this macroscopic equation or these macroscopic properties. We want to know what's going on in terms of the behavior of the individual particles, the individual molecules that make up this gas. Inquiring minds want to know what the temperature means when we talk about individual molecules. Right? And that's also what Maxwell and Boltzmann wanted to know. They wanted a microscopic explanation for PV equal nRT. And to do so, they put forth a theory, and it's called the kinetic theory, or the kinetic theory for the behavior of gases. And that's exactly what we're going to take a look at here, is this kinetic theory. We're going to do what they did. All right? Basically, this kinetic theory allowed properties of gases at low pressures to be predicted. And it allowed an understanding of why some of the properties of real gases at higher pressures deviated from this ideal gas law. But more importantly, what it did is that it allowed the quantity, pressure times the volume here, to be understood in terms of the motions of the molecules. And it provided a means to understand this concept of a temperature in terms of the motions of the molecules. And that's what we're going to look at today. We're going to see how we can describe pressure and volume in terms of the motion of the molecules, and temperature in terms of the motion of the molecules. That's our goal. All right. So in order to do that, the first thing we have to do is to understand what we mean by pressure. So for example, if you have some gas here in a container, there is some gas, and you're measuring the pressure of this gas in that container. Well, what you're really measuring is the force that the gas exerts on one of the walls of this container. That is, pressure is the force exerted by the gas on one of these walls. So it's the force per unit area that is exerted on the walls of that container. That's what pressure is. Okay. But now, what Maxwell did, and this is 1850, 1855, what he did is that he recognized that he could understand this macroscopic pressure in terms of the individual forces of the molecules when they hit the container. So in other words, he proposed that this gas was composed of these molecules, and that these molecules were moving. That was his proposal. And that when they moved and they hit the walls of the container, well, that was the force that was exerted by the gas. In other words, the force was really the individual forces, F sub I here, of the individual molecules. That total force was the individual force of the molecules hitting the walls of the container. That's what led to this macroscopic concept, the macroscopic quantity of pressure. All right? So that was his idea. Okay, well, if that's the idea, he carried it through now to a prediction. All right, so the idea is this force arises from the individual forces of these individual molecules hitting the walls of the container. Okay, so let's look at what theory he wrote down. Okay. I think I turned that off. Okay, so let's look at what theory he wrote down. Well, his goal here was to calculate these individual forces, F sub I. And, of course, go back to classical mechanics. The force is the mass times the acceleration, the mass of the particle, the molecule, times its acceleration. And acceleration we can write just in terms of delta V over delta T. So that's just the mass times delta V over the change in time. And if the mass is constant here, well, then this numerator, that's the change in the momentum. The change in momentum per unit change in time. That's what this force is. So what we have to do here is we have to calculate the change in the momentum of the wall when the molecule hits the wall. That will be the force of the individual molecule in the wall. Right? That over the time between the collisions of the molecule with the wall. That's the individual forces. That's what we're trying to calculate right here. All right, so let's do that. Let's calculate delta P. The change in the momentum of the wall, the change in the wall's momentum. So let's do it in one dimension first. So here's our box, and this is just a cross-sectional view of that box I drew over here. And this is going to be the wall that we're going to be interested in. All right, the box has a length L. And we got this molecule with some mass M, and it's coming into the wall. It's going to collide with it. And it has some velocity vector V. But let's do it in one dimension, because it's simpler to do it in one dimension, and then we're going to extend it to 3 dimensions in a few minutes. All right, so we're just going to do it in one dimension now. So we're only going to be interested in then the x component of the velocity of this molecule coming into the wall. And we want to know what is the force exerted by this molecule when it collides with this wall. So first we got to get the change in the momentum. All right, so this molecule comes in, and it hits the wall, right? And we're going to consider it to be an elastic collision. So if the component of the velocity in the x direction before the collision is v sub x, then after the collision, it's minus v sub x, right? We've just changed the direction of our velocity vector, not the magnitude. Okay. So the change in the atom's momentum, then, is just the momentum after minus the momentum before. So the momentum after was m times minus v sub x. Momentum before m sub v sub x. So delta in the change in the atom's momentum is minus 2m v sub x. Okay. However, we got to conserve momentum. So the momentum change in the atom plus the momentum change in the wall has to equal 0. And what we want to know is the momentum change in the wall, because we're after this macroscopic quantity pressure. And so if delta, the change in the momentum of the atom, is minus 2m v sub x, well then the change in the momentum of the wall is 2m v sub x. All right? Okay, so we got one quantity here. We've got delta p. But now we have to calculate how often that momentum in the wall changes due to this molecule's collisions. All right? So of course, we need the delta t. And so what happens here? Well, the molecule comes in, collides, and then it reflects. And the molecule's now going in this direction where it hits the back wall, and then it reflects. And then ultimately it comes back and hits the front wall. And what we want to know is, what is the time here between the collisions? The time between when that molecule makes the momentum in the wall change. All right, so what is this time, delta t? Well, if we know the length of the box and we know the value of v sub x, well, we can calculate that time. That time is just 2 times the length of the box, because that molecule's traveling back and then forth. That's 2L, divided by the velocity component in the x direction, v sub x. That's delta t. All right? So now we've got delta p and delta t, and we can plug that in and make it simple a little bit. And so here is the force exerted by the collision of one molecule on the wall, that one wall of the container, mv sub x squared over L. Okay, but we said that Maxwell's idea was that macroscopic total force was the sum of these individual forces. So what we have to do is we got to take the force of each individual molecule and add them up over all the molecules. So there's that force for molecule 1, for molecule 2, molecule 3, all the way up to molecule N. Okay? And now I'm going to pull out an m over L out of this. All right? So I just pulled out an m over L, and I have left the sum of the squares of the velocities in the x direction for each one of the molecules. Notice here in this treatment we have identical m's. The particles are the same, but, and this is important, the velocities of the molecules are not the same. All right? That's going to be important. Okay. Now, this expression here, I want to simplify a little bit. In particular, I want to simplify the sum of the squares of the velocity components in the x direction for each one of the molecules. So to do that simplification, I'm going to introduce this quantity. This quantity is the average of the square of the velocity in the x direction. All right? So what this means is I take the velocity in the x direction, I square it, and then I take the average. This is not the square of the average velocity in the x direction. That's different. This is the average of the square of the velocity in the x direction. So how am I going to evaluate that quantity? Well, the way I'm going to evaluate it is I'm going to take the velocity in the x direction for molecule 1 and square it, and add to that the square of the velocity in the x direction for molecule 2, and add to that the square of the velocity in the x direction for molecule 3 all the way up to molecule n. And then if I want the average, I'm going to divide by n, the number of molecules there are, right? Okay. Now, I'm just going to bring n here over to the other side. So I have n times the average of the velocity in the x direction squared is this sum. And this is exactly the sum that I had in my expression for the total force. Hey, I can simplify that now, right? There's that same expression. Here's my total force. So what I'm going to do is I'm going to substitute n times the average of the velocity in the x direction squared in for this whole sum, and I have now something that's much more tidy. Okay? So that's the force exerted, the total force exerted by all the collisions of the molecules in the container on that front wall. Okay, but now I want the pressure. And the pressure is just force per unit area. And so I'm going to take my expression for the force and then divide it by the unit area. The unit area here is this, or the area is the area of this wall here in my initial example. I'm going to call that area A. And if this is a cube, and I'm going to make it a cube because it's easier to do it that way, the area times the length then of this box is just the volume. All right? So here's the volume. So there's my expression for the pressure due to all of the molecules colliding with the front wall of that box. However, this is an expression for the pressure in one dimension only, the x dimension. And we know in real life we got 3 dimensions. And we got to take care of that. So let's do that now. Let's extend this problem to 3 dimensions. To do so, we're just going to realize right here, extend to 3 dimensions. Okay, it's a little slow. We're going to realize that the square of the velocity, right, is the sum of the squares of the components. That you understand. That's okay. What's not so obvious is this, that the square, or that the average of the square of the velocity is the sum of the average of the squares of each one of the components. That is true. You can prove that. We're not going to prove that. I won't hold you responsible for proving that, but that is true. Okay? All right. Now, that's correct, but now here comes a critical assumption in Boltzmann's treatment. And the critical assumption is that the motion of the molecules in this gas here, that motion is random in the sense that the molecules don't have a preferred direction. They're going in the x direction as often as they're going in the y direction, as often as they're going in the z direction. So the motion is random. If that motion is random, well then, on the average of the velocity squared in the x direction is going to be equal to that in the y direction, is going to be equal to that in the z direction. Okay? If that motion is random. And that's great, because it's going to make things a little more simple for us up here. Hey, if that's right, well then the velocity, the average of the velocity squared is 3 times the average of the velocity squared in any one of the dimensions. Okay? Hey, that's going to make it easy to extrapolate this to 3 dimensions. Okay? Because now I'm going to be able to substitute into here, which had the average of the velocity squared only in the x direction. I'm going to be able to substitute in an expression for the velocity, or the average velocity in 3 dimensions. That's just going to be 1/3 that. All right? From this here, this is going to be 1/3 the average of the velocity squared. Okay, that's great. So now I'm going to do that substitution way up into there. All right? And when I do that, hey, look at this. I have a result. This is the kinetic theory result. We just did exactly what Maxwell did. We have an expression for the pressure times the volume. That pressure times the volume is written here in terms of the average of the velocity squared of the molecules. It's written in terms of the motion of the molecules. For the first time, there's an understanding here of what gives rise to pressure. And that is the velocity or the motion of these molecules hitting the wall. Okay? Hey, that's great. That's the kinetic theory result. But now, Boltzmann also knew from experiment that P times V is equal to nRT, right? That's the experimental result. That had been known already for over 100 years. That's the experiment. So if his theory is correct, if PV is equal to nm average velocity squared over 3, well then nm average velocity squared over 3 better be equal to nRT if his theory is correct. That will give us here a prediction for what the velocity of the molecules ought to be in terms of something experimentally controllable. So we can see if this kinetic theory model is correct. Okay? Okay, so we can solve this for the average of the velocity squared. It's equal to 3nRT/n over m. Hey, we can go in the laboratory, vary T, and see if in fact the average of the velocity squared of the molecules is equal to this expression here, right? That's great. We got a way to experimentally check this theory. And you also see here now a relationship between the velocity of the molecules and this macroscopic quantity temperature. Hey, temperature is related to the motion of these molecules. Okay? Okay, but before we go on, this is kind of a messy expression here. It's got too many n's and m's in it. So let me simplify that a little bit for you. Okay? I'm going to simplify this so that this is 3RT over capital M, where the following is true. Over here, N is the number of moles in the gas. That's little n. Big N was the number of molecules in the gas. Little m was the mass per molecule. All right? So all of this is equivalent to 1 over big M, where big M is kilograms per mole. You can convince yourselves of this equality. So I'm taking all these N's and M's and making one big M. Okay. So now that's my expression here. So I have the average of the velocity squared is equal to 3RT over M. All right, but this quantity is the average of the velocity squared. It's more convenient for us to talk about a quantity proportional to the velocity and not the velocity squared. So what I'm going to do is I'm going to take this and I'm going to take the square root of it. That's simple, right? So I now have the square root of the average of the velocity squared. That's the square root of 3RT over m. And I'm going to call that the root mean square velocity. I'm going to put an RMS here in as a subscript for the velocity. It's the root mean square velocity. I wanted to talk about a quantity proportional to the velocity instead of the velocity squared. That's all I did there. That's the root mean square velocity. Okay, but the other big thing about it here is you can see for the first time that now we've got, and Maxwell had, an understanding of what temperature was. Temperature is related to the motions of the molecules. Temperature is related in this way to the speed of the molecules. Those are the two important results. And this kinetic theory makes a prediction for what those velocities ought to be. Okay. But in addition, the temperature is a measure of the kinetic energy of the molecules. How's that? Well, it is for this reason. Here's the expression we derived from the kinetic theory. And then here is an expression that I just wrote down that says the average energy, the average kinetic energy of a molecule is 1/2 m, where m is kilograms per mole, times the average of the velocity squared. So if I substitute the average of the velocity squared into here, I get 3/2 RT, right? Hey, this is telling us right here that the temperature is also a measure of the kinetic energy of these molecules. Okay? So we're getting a microscopic view here of what temperature is. It's related to the motions of these molecules. Now, before I go on talking about this, let me make one big point. And that is that this expression here for the average energy, notice that it's 1/2 m times the average of the velocity squared. It is not 1/2 m times the square of the average velocity. Okay, this is important. The average energy is not the square of the average velocity. Rather, the average energy is the average of the velocity squared. There's a big distinction. This is because the average energy is the second moment of the velocity distribution function. Variables don't always correspond in a one-to-one manner. You don't have to understand that if this is foreign to you, but I do want you to know that this is correct. Okay? Okay. So now let me pick up back here. All right, so what I want you to notice is that the root mean square velocity is got a mass dependence in it. So what does that mean? Well, it means the following. For some constant temperature, say we pick 300 degrees Kelvin. At some constant temperature, the velocity of the molecule is going to depend on its mass, and it's inversely proportional to the mass. So heavier molecules move more slowly. Lighter molecules move more quickly. So for example, helium at 300 degrees Kelvin, hey, it's cruising along at 3,060 miles per hour at room temperature. Xenon, on the other hand, which is much more massive, is moving at a measly 534 miles per hour. There's a mass dependence here. Okay? However, there is no mass dependence to the kinetic energy. Hey, the kinetic energy we saw was 3/2 RT. Hey, you don't see a mass dependence in here, do you? The kinetic energy is only dependent on the temperature. So whether or not you have helium or xenon, the kinetic energy of those molecules is of those atoms is 3.74 kilojoules per mole at 300 degrees Kelvin. Doesn't matter that helium's moving 6 times as fast as xenon. They both have the same kinetic energy. There's no mass dependence in the kinetic energy. Now you say, oh, but hey, look at this. Here's a mass. There's a mass dependence. But no, because you have to remember that if you substitute in here if you square this, there's an m here, that cancels. So there's no mass dependence in the kinetic energy, but the velocity is dependent on the mass. Okay? That's important. Okay, well, so I told you that this was the kinetic theory result. That is, that the root mean square velocity of these molecules was represented by this equation. And from this equation, if you calculate at 300 degrees Kelvin, these are, in fact, the velocities of those atoms. But how do we know this is right? How do we go and measure the velocities or the speeds of molecules or atoms? Well, this is the way we do it. It's called a time of flight technique. Are we all on board here? Questions? Okay. So how are we going to do this? Time of flight technique. What we're going to do is we're going to have a little pinhole here that we can open and shut really quickly. So we're going to let out a little pulse of gas. And to measure the velocity of the molecules, we're literally going to measure the time it takes the molecules to fly from where we let them out to some detector. And since we know the distance, hey, we're going to be able to calculate the velocity from that. All right? So the idea is at time t equals 0, we let out a little pulse of gas, and then we start a clock running, and then we just measure how long it takes the molecules to fly from this origin here to this detector. And since we built the apparatus and we know what L is, hey, we can calculate the velocity. All right, time of flight, that's what is done. All right? Okay, however, when we let this little pulse of gas out, and now we let the molecules fly to that detector over here, what happens as a function of time? Well, what will happen is that pulse of gas will spread out. That pulse of gas will spread out because not all of the molecules or atoms in that pulse of gas have the same velocity. Some of those atoms are moving faster than the other atoms. And so what's going to happen is that the molecules or atoms that are moving faster, hey, they're going to hit the detector first. The molecules or atoms that are moving more slowly, they're going to hit the detector at a later time. And that's what we also want to know, is this distribution of velocities. Okay, but in the measurement, what we're going to measure is a distribution of times. So out of our detector, we're going to have a plot that looks like this. This is going to be f of t, well, that's essentially the number of molecules hitting the detector at a certain time t versus the time. So when we first let our pulse of gas out, well, that's time t equals 0. All right? And then for a while, there are no molecules hitting the detector because, hey, it takes a while for them to get over here to this detector. But then all of a sudden, they start reaching the detector. And this is essentially just the number of molecules that hit the detector as a function of time. That number of molecules increases, it becomes a maximum here at some time, and then it exponentially decays here. Okay? So this is what we measure. This is a distribution here of flight times of the molecules in this pulse of gas. Well, that's nice, but this is a distribution of flight times, not a distribution of velocities. And hey, we wanted a distribution of velocities. We want to know the velocity here of these molecules. So, well, you know how to convert time given the path length to velocity. But it's not so straightforward because we got a distribution function. We got a distribution in time, and we want to convert that to a distribution in velocity. We got to change the variable here in a distribution function. So how do we do that? Well, the way we do that, we want this f of t to be an f of v. All right? Well, we recognize here that this distribution in time, the probability of finding a molecule between t and t plus dt, has got to be equivalent to the probability of finding a molecule with a velocity between v and v plus dv. Right? But to get from one distribution function to another, for example, if we want f of v, what we have to know is how one variable changes with respect to another. So we need to know what this. We have the distribution function. Just a second. Okay, we have this distribution function f of t, but we need to know how t changes with v. We need dt by dv because we need that. So let's get it, right? I'll tell you why in a moment. Okay, so we know how v changes with t. So we're going to take the derivative of v with respect to t and then turn things around. All right, so dt dv is proportional to minus t squared over L. This is telling us essentially how the variable t changes with v. So to every point in our time of flight distribution, we're going to multiply this by this, what's called a Jacobian. We need this because the time and the velocity don't correlate in a one-to-one manner, right? That often happens with two distribution functions. Now, if you don't understand what I just said, it's okay, right? All right, this was just some extra. I don't hold you responsible for it. All right, I just changed my variable in the distribution function. Yes? Yes, I think in the notes I might have had as a proportionality. Up here I actually have the equal sign. Yeah. That actually won't matter in this transformation. Pardon? Yeah, no, I understand. Right, that's fine. Yeah, if I don't have the equal sign there, that's why I left it out there, I think. Okay. All right? Okay. So anyway, this is the velocity distribution. You don't have to understand how I got there. This is what the velocity distribution looks like. It's what's called the Maxwell-Boltzmann velocity distribution. And the bottom line is that Maxwell-Boltzmann predicted this about 1855. They actually predicted this distribution function, right? We didn't predict it. We didn't go through that part of kinetic theory, but they predicted it. However, it was only until 1955 that the technology existed, fast enough timing electronics existed to actually measure this experimentally. So this took 100 years or so in order for this distribution function to actually be measured. Okay, but here it is. F of v. First of all, there's all of this stuff, which is proportionality constants. We'll talk about that in a moment. But the variable here is v squared, right here, and times an exponentially decaying function with a v squared in there. So what does that mean? Well, if you're looking at the form of f of v, this v squared, hey, that's what gives rise to this increase in f of v right here at low velocities. That's a quadratic, v squared. But you're multiplying it by an exponentially decaying function with this v squared in the argument. And so that's what gives you this tail, right? So if you're multiplying a function that's going up and one decreasing, you're going to get a maximum at some value of v. All right? So that's where the shape of the Maxwell-Boltzmann distribution function comes from. And what this is telling you is the probability here of finding a molecule in a gas with a speed between v and v plus dv. That's what that's telling you. Okay. Now, we often characterize here this distribution functions by some quantities, and one of those quantities is what we call the most probable speed. So here's the distribution function, and I have the most probable speed labeled. The most probable speed, VMP, is simply the value of v at which the probability is the largest. Hey, that was like our most probable value of r in the radial distribution functions. That's what the most probable speed is. If you wanted to get that mathematically, what you would do is you take this distribution function, take the derivative, set it equal to 0, and then solve for v that makes that derivative equal to 0, right? The derivative is 0 at maxima or minima. And then you would find that the value of the most probable speed is the square root of 2RT over m. You're not responsible for taking this derivative and setting it equal to 0. You are responsible for knowing physically what the most probable speed is. The fact that it is this value here where the probability is the largest. It's the most probable value of v. And you're responsible for recognizing this, right? I don't ask you to memorize it or write it down, but if you see it, you should know what it is. Okay? All right, so that's one quantity that we use to characterize this distribution function. Another quantity that we use is the average speed. V bar, average speed. And the first thing that you see is that the average speed is a little bit higher than the most probable speed. All right? It's a little bit larger. Why is that? Well, it's a little bit larger because on these Maxwell-Boltzmann distribution functions, there are molecules way out here that have very high speeds. There are not a lot of molecules that have very high speeds, but there are molecules with very high speeds. And so when you average over this distribution function, because there's such a long Boltzmann tail here is what it's called, the average velocity is going to be a little higher than the most probable velocity. All right, so that's physically why the average velocity is a little bit larger than the most probable velocity. That's important. If I wanted to calculate what the average velocity is, I would take the distribution function, multiply it by v, and then integrate over the range of v, which is 0 to infinity. You don't have to do that. But the quantity that you would get if you had done that is the square root of 8RT over pi m. All right? It's larger than the most probable value. And then finally, the other way we characterize the distribution function is by this root mean square speed that we've already talked about a lot. That root mean square speed here is even a larger value than the average velocity or the average speed. And the reason for that is, again, because of this Maxwell-Boltzmann tail. Hey, we got molecules here that have very high speeds. We don't have a lot of molecules with high speeds, but we got very high speeds. And when we take that speed and we square it, and then take the average, hey, they make a big contribution, and they push this root mean square speed even higher than the average speed. All right? And then again, if you wanted to calculate what that is, you'd take v squared, multiply it by the distribution function, integrate it over all values of v, and you'd get what we got before, the square root of 3RT over M. All right, so bottom line here, for argon at 300 degrees Kelvin, the most probable speed is 353 meters per second. For argon at 300 degrees Kelvin, the average speed is 399 meters per second. And the root mean square speed, well, that's 433 meters per second. So here you can see how these three quantities increase as you go from most probable to the root mean square speed. All right? And in fact, no surprise, if you actually go and measure the argon speeds distribution function, then evaluate these characteristics, you find that indeed those measurements agree with what Mr. Maxwell and Boltzmann predicted, you know, in 1850, 1855. No surprise. Okay? Okay. Now, back to this distribution function. We saw how to characterize it, but I want to talk about a couple of other parameters that it has in it. It has in it the mass, and it has in it the temperature here. So let's talk about what this distribution function looks like for different masses and different temperatures. That's the general form, but different masses and different temperatures. So let's start by keeping the temperature constant, 300 degrees Kelvin, and now we're going to look at the distribution functions for three different masses. And I'm going to plot that. Here it is for xenon. So what you can see is that xenon, very narrow distribution. Here it is for argon, lighter mass, broader distribution. And here it is for helium, really broad distribution. Well, first of all, you can see that the average speed of helium is much greater than it is for argon than it is for xenon, because we already saw that that was inversely proportional to the square root of the mass. But the other thing to note is how broad the distribution is for helium, right? How broad it is compared to xenon. And that's the general case. The lighter masses have broader distributions. Hey, the helium is so broad, meaning that there are helium atoms here that are so fast that this is the reason why there's relatively little helium and hydrogen in our atmosphere. And that is because at our temperatures, right, there are enough molecules with high enough velocities to escape the Earth's gravitational pull because they're here at the tail end, right? And so the helium and the hydrogen leave our atmosphere, unlike Jupiter, which is 300 times more massive than the Earth, where the gravitational pull is greater. And in that case, then those helium atoms don't have enough velocity to escape the Earth's gravitational pull. Okay? Okay, so that's mass. Now, what about temperature? So now we're going to keep the mass constant, and we're going to look at temperature. So here's the distribution function at 100 degrees Kelvin. Hey, pretty narrow. Here's the distribution function for argon at 300 degrees Kelvin, broader. Here's the distribution function at 1,000 degrees Kelvin, broader again. So again, you see that as we increase the temperature, hey, the average speed increases. As we increase the temperature, the width of that distribution function increases. Now, one thing to note here is this is a probability, right? So the areas under these curves have to all add up to 1. So if this distribution function is going to move to higher velocities as we increase the temperature, well, of course, then this maximum probability is going to have to go down because we can't lose any molecules. So all the area under this curve at 100 degrees Kelvin has to equal the area under this curve at 1,000 degrees Kelvin, right? Because this is a probability that we're plotting here. Okay? All right. So that's our description of the Maxwell-Boltzmann distribution. See you on Friday.